to your tape out. So the first thing you do is you do a schematic capture because you have an idea that I want to design a NAND gate. So you say a NAND gate I will want to make like this. A, B, A, B, and these are PMOSes. This you may say is Y. Okay. So this is the schematic. After you made the schematic in the schematic capture, you will analyze this. How will you analyze this? You will give different stimuli to A and B, and you will see if your output is coming correctly or not. That is simulation. After you have verified that the schematic is working fine, at least on the schematic level, I'm getting the functionality that I wanted, the kind of delays that I was targeting, I'm able to achieve them. Then you go to the layout. You implement this in the form of a layout. Okay. So you will design a few PMOSes, you will design NMOSes, you will connect them. So don't worry, you will do all of this. I will make you do all of this. But yeah, okay. So this is the layout. Once you've made the layout, you see that are all the design rule checks. Now, what do you understand by design rule check? Anyone?
Sir, this talks about the set of rules that has to be followed in designing a particular layout.
Yeah. So look at it like this. I ask you to draw two parallel lines on a sheet of paper, as close to each other as possible without them even touching ever. So you do realize that there is the second line that I drew, it went a little wavy because I was worried that it should not touch the first line. So you do realize that if you have a kind of instrumentation, I did not use a scale, but if I use a ruler, I can probably draw them a little bit still closer. But then, if the tip of my pencil is not sharp, I will draw them a little farther away. So there are so many instrumentation reasons because of which I cannot draw these two lines closer than a minimum spacing. Because if I try to do that, then somewhere there is a possibility they will short with each other. Are you able to see this? So this minimum spacing that we have to keep between any two rectangles that we just made here is called design rule check. Now, these are design rules, and we should not be violating any of these design rules. Otherwise, when we fabricate on silicon, there could be a loss of functionality somewhere. So as you make the layout, you also simultaneously do the design rule check, DRC. We call it DRC. Okay. Then we do what is called as layout versus schematic check. What is layout versus schematic check? This check means that, see, I had this circuit in my mind. And I am trying to implement this circuit in a layout. So I said this is ground, this is VDD, but it could happen that I've made some connection wrong somewhere. So to verify that this layout actually represents the schematic that I had intended to draw, to implement, is called as layout versus schematic check. Okay. So what did we do? When we were going down from schematic to layout, we did a verification. What was the verification? That I should run a simulation and see that my schematic is operating as it is expected to be. And then once we have done the layout, we again do a verification that this layout is representing the same functionality as the schematic wanted to. So verification is not just done downwards, it is also done backwards. This you noticed even in the chip implementation flow last time, where we said that once we have the post layout stuff, we go back to the STA stage and see that even after the post layout, things are still fine. You remember that? So we do lots of to and fro runs to ensure that things are as they were expected to be. And this layout versus schematic is one such back and forth run. Is that okay? Any questions? Vaishnav, you have a question?
Yes, sir. Sir, while we are doing layout, I mean, like we can drag it into anywhere. I mean, like giving some space, some area, or more area. So how do we
So
end up
area is
saying?
gold. Wait. Area is gold. You want to
Yes.
give more area?
I mean, like it's not what I meant exactly. I mean, like we can do whatever we want, avoiding the errors, right, sir? I mean, like there are many possibilities that we come to a conclusion. So my doubt is that how can we say that our model is much efficient?
So minimum area?
Uh, okay. So I mean, like
Because
would
area is gold.
any, yes, sir. Would there be any kind of I mean, like any kind of option that we can check our area in the I mean, like in the DRC or LVS check? Uh,
No. So no. That is not available. You just draw. And then the competition will tell that your area is good or bad.
okay. Okay. Thank you.
Suppose you join Intel and you draw something, or let us say you join Synopsys and you make a layout, then ARM is also working on the same technology, or ST is also working on the same technology. They will also be making their layouts.
Yes.
Some customer will come back to you and tell you your area is bad. We don't want to use your library. We'll go with ARM.
Okay. Okay. So it's like a
It's already too late. It's already too late when you get this information.
okay.
The customers are already lost.
Okay. Okay.
So
Thank
don't
you,
wait for that benchmark. Always strive to make a very dense layout, as dense as possible.
sir. Okay. Thank you.
Okay?
Yes, sir. Thank you, sir.
Yeah. You can lower your hand. Yeah. So once the layout versus schematic thing is done, then we do what is called as a parasitic extraction. See, till the time we were in the schematic phase, did you even talk about the capacitance of this wire A and how this wire A capacitance is coupling with the output? No. You could make something, but usually you would not do. You simply say A is the input and Y is the output. But over here, when you make this layout, you see that there is an input A coming over here. There would be some metal over here, which is running very close to my output. So there is bound to be some capacitance. I need to extract that capacitance and see its impact on my results. So that is the next step. After LVS is done, we go to the step of parasitic extraction. So all the parasitic resistances and capacitances can be extracted. And okay, in this course, we will not look into these two aspects. Okay, but we will, after parasitic extraction, go to post-layout circuit analysis. Those two aspects are valid when we are talking about circuits like IOs, where package, what kind of package is being used also comes into picture, and IOs being analog in their characteristic, the substrate coupling, etc., also becomes big. In this course, since we are going to work on digital circuits, so substrate noise and package model thing do not really bother us in this course. Okay. These are separate independent job profiles. The package model extraction and verification, this is a separate job profile in itself. We will not be covering it in this course. And once we've done the post layout circuit analysis, check that the delays are in line with my specification even after these extra parasitics had come into picture. That is when we say that my circuit is complete. I can go ahead for a tape out. Okay. There's a question. Yes, Meher.
Yes, sir. What do we exactly mean by substrate coupling?
So substrate coupling is, let us say I have a processor over here on one side, and there's a, let us say this is a big chip. I have a processor over here, and let us say there is a PLL over here somewhere. Now, since this is the same chip, they are sharing the same substrate.
Yeah.
Now, if the processor is operating at, let us say, 2 gigahertz, there will be some currents which will flow into the substrate.
Yeah.
Those currents have to be sunk somewhere. There is a very high probability that the noise injected by this processor will impact the functionality of this PLL. So when you're designing that PLL, you have to see that there is no substrate noise, or even if there is a presence of substrate noise, your circuit should work well even after that.
Right. So it's like, source to body capacitance and so on. We're taking account for that.
Yes, because source to body junction capacitance will always exist. Junctions would toggle, so there would be some current in the source, and that can lead to noise for the other circuits which could be sensitive to that noise. In this course, since we are looking at digital circuits only, such noise is not really bothersome for us.
Right. Okay. And how do we solve these problems?
Okay, so we use things like guard rings. So guard rings are so if let us say this is your NAND gate, let us say this is some analog circuit. So what I will do is around this analog circuit, I will make a ring or substrate connection. Okay, so if there is any noise coming from anywhere else, because this ring has all VDD substrate connections and ground substrate connections in it, this ring will sink that current. It will not let that current spoil the behavior of the transistors enclosed within it.
Okay. Okay. Yeah.
Okay. There is another technique which we call as deep and well or triple well technology. We will not look into that just yet, but there are many methods. At a designer level, if you want to do something, you can work with either triple wells or with guard rings. Guard rings are more appropriate when you do not want to lose area. You know, when these circuits have to be placed really close together, then guard rings are denser.
Right. Okay. But wasn't the problem, that the current was flowing into the substrate? So like,
Yeah.
so how it so if the guard ring is also a substrate.
Yeah, but it is giving it a power supply, na? The guard ring is fully connected to VDDS or GNDS or whatever is the substrate supply. Very richly connected. So no noise from the analog circuit can go to the digital side, nor from the digital circuit come to the analog side. Because there is such huge sync, such good connectivity to substrate power in this guard ring.
Thanks. Yeah.
Okay. So we move forward. Any other questions? Oh,
so, one more thing.
Yes.
Can I ask?
A moment.
Yes, sir. I want to ask, can we not make the area of the layout minimum by, when we are in the DRC step, we can check the minimum width and area of we could check the minimum width and area of the poly and all other things. So by that, can we not make the area of the layout minimum?
Yes, that is the way.
Minimum width and
that is the way. See, Vaishnav was saying that you have such a big field, draw your devices anywhere. Why will you anywhere face an error? I said, yes, you will never face an error, but then you will lose area. So you design minimum area at minimum DRC and go ahead. Okay. Yes, Faisal?
Yes, sir. So if we get to know about this parasitic capacitances, then how will it affect our circuit and how we'll get rid of them?
Oh, you tell me if there is an RC in a circuit, what happens?
It affects the delay.
Yes, so that is how it will affect the circuit. You targeted a timing of say 500 picoseconds, but there is a capacitance there, so the timing changes to 550 picoseconds.
Yes, sir. And then how will resolve this issue?
We will increase the width of the devices so that this extra capacitance can also be, handled.
Okay. Okay, sir. Got that.
Okay.
Thank you.
Yeah. Gagandeep?
Sir, in the post layout circuit analysis, internally, sir, what will happen? Sir, post layout circuit analysis में, so sir, necessarily this will happen कि I will take that netlist and the tool will I mean insert all the parasitics that have appeared and then it will simulate. Is that what happens?
Yes. So in the post layout circuit analysis, all the our resistances and capacitances that are parasitically present in your netlist would be embedded into the design, and then you simulate again. So your design would actually have this capacitance there. It will have a capacitance from B to output. It will have a capacitance from B to this internal node. You will have a capacitance from A to this internal node, and so on. So post layout netlist will have all the capacitances in picture, and then we will simulate. It will also have some resistance between ground and you know your NMOS there. Okay. Yes, Divya.
Good afternoon, sir. Basically, I want to know what we are exactly doing in parasitic extraction. I don't get it.
So do you realize that when you will make the wires to make these connections between A and the gates of the two transistors and so on, these wires will have some capacitance of theirs?
Yeah.
These wires are metal plates. So when there is some capacitance there, would you not want to see the impact of that capacitance on circuit behavior?
Yes.
So the first step to see their impact on circuit behavior is to measure or estimate the value of this capacitance.
Yeah.
That is what parasitic extraction step does.
Okay. So will it create any issue or not? Like what?
No, we do not even know that. Parasitic extraction step only estimates the various capacitances. Whether it is creating an issue or not, we check that in the post layout circuit analysis.
Okay.
So,
Okay.
so
yes,
yeah. So the temperature factor is also checked in post checks.
Yes, has to be.
Because estimating temperature cannot be like, is it possible by looking at the previous models?
So you can say that my circuit has a functional specification to operate fine between 125 degrees Celsius and minus 40 degrees Celsius.
Okay.
So you have the specification. You check in that specification range.
Okay, sir.
Sir, am I audible?
Yes, Akash.
Sir, as you mentioned,
Vaishnav already had his hand raised. If it's not linked to what Akshay just asked, then can you wait?
It is linked, sir. That's why I'm asking.
Okay.
So as you have mentioned, we considered the effect of parasitic extraction in the post layout circuit analysis. So after considering, if we see that there is some effect, then we again go to previous step and consider this effect before taping it out.
Yes, then we go back to the circuit stage, schematic stage. We say that I want to increase the size of this particular NMOS because the output capacitance is very large. The NMOS size that I have put yet will not be able to drive sufficient current and give me the timing that I am looking for. So I increase the size in the schematic. I then change the layout. I then again do DRC, LVS, again extract, and then resimulate. The entire loop has to be done again.
Okay, sir.
Vaishnav?
Sir, yes, sir. So, sir, when we get to know about the parasitic extraction, then are we connecting these capacitors manually by ourselves in layout again? Or would there be any kind of option for us to check this parasitic extraction after LVS check?
See, in the layout, you made those wires already. So those parasitics are already there. You don't need to do anything else. They're already there. They're parasitics. They're not to be designed. They're parasitics. They just appear. They're parasites. Wire बनाई तो उसके साथ एक parasite आ गया.
Okay, sir. So then why don't these I mean like show up in design rule check and layout versus schematic, sir? I mean like during those, even these parasitics are present, right, sir?
Yeah.
So I mean like the outputs which we get are included with these parasitic extractions, or I mean, like, are they excluded with this parasitic extraction?
So output of what? Output of design rule check.
Yes, sir.
No, design rule check is a different tool altogether. You do design rule check with caliber, and you do parasitic extraction with a different tool. Let us say RC extract.
Okay, okay, sir. So after layout, now if we check the output, I mean, like any output, for example, we have done CMOS inverter over in our refresher. So after layout, I mean, like if we take the output, so the output would be with respect to parasitic. I mean, like the output we get would be including the parasitic extractions, or I mean, like the
So
capacitance included.
it will include if you have done the extraction and embedded the capacitances into your netlist. If you're doing the post layout circuit analysis, it will include. You made the layout, left it there, and then you're redoing the simulation of the schematic again, then no change.
So, sir, then I mean, like we have already got our output. So then I'm like, why are we doing this parasitic extraction again, sir? I'm like, we already know. I'm like, at which time our circuit is getting worked, and at which time it's getting turned off.
So yeah, first tell me one thing. Tell me one thing. In the first schematic that you made, are you sure how much is the wire capacitance?
No, sir, I'm not sure. But
so
however,
you have not put that capacitance, or even if you have put that capacitance, could be wrong.
But the output which we get would be included of this capacitance, right, sir? I mean, like,
so to be able to get that output, you have to do a parasitic extraction, na?
Sir,
so how will you estimate the capacitance? The layout is simply rectangles.
Yes, sir. The layout is simply rectangle.
So rectangles don't tell you anything.
Yes, sir. But the output which we get at layout is
simply rectangles. No, it is simply rectangles. Layout is simply rectangles.
For suppose in ELDO, we give this code called EZ wave, and we get to know this waveform analysis, right, sir? If we consider.
So you will go through the entire flow again. Don't worry. So you will see that DRC is a separate step and parasitic extraction is a separate step. If you do not do parasitic extraction and only do, let us say, until LVS, okay, then you will not be able to add these extra capacitances in your netlist. You will never be able to see the impact of those capacitances on your circuit behavior.
Okay, we just want to know the effect of this specifically on the circuit.
Yes.
Okay. I'm like, now I understand, sir. I was thinking only about I was only concerned about the output, but not about this exact effect of this capacitance.
Look at it like this. Without these capacitances, the delay could be 500 picoseconds, and that could be well within your specification. As soon as these capacitances come, you need to increase your delay increases to 550 picoseconds, which could be out of your specification. So what do? Akash is asking this in the chat window also. What do? I said you increase the size of your NMOS and your PMOS so that it can now sink more current.
Yes, sir.
When you increase the size of your NMOS and PMOS, what does it do? It increases the drive capability of these devices. So they can now sink or provide more current. So that extra current can discharge this extra capacitor also within the stipulated time. That is why you will come back within the specifications.
Okay, sir. I understand.
Akash, does that solve your problem?